Hello students, as per the digital education initiative of APJ Abdul Kalam Technical University, here is another lecture of the series for the subject VLSI technology having subject code KEC 053. The topic for the lecture is metallization, that is the next process step as a part of IC fabrication. The contents of the lecture include metallization, what are the applications of metallization, the properties, that is desired properties expected from the metal during the process of metallization, or desirable properties of the materials required for the metallization, and the choices of the metals which are used in IC fabrication. As a learning outcome, I expect you to be able to narrate the need for metallization, and you should be able to list out the properties of the materials which are required or essential properties which are needed when the material is to be used for the purpose of metallization. You need to know the applications of metallization, and you should be able to distinguish between basic metallization techniques based on their features, advantages and disadvantages. So, you should be able to make use of proper choice of material, as well as you should be able to achieve, or you should be able to suggest desirable technique which can be used for metallization. So, what is exactly the metallization means? In case of my integrated circuit fabrication, this is the last stage where we need to, after finishing the designing of different devices, you need to interconnect them, and this interconnect of individual devices as well as between the two devices, that is to form a circuit, whatever interconnections are to be established, that is being done by metallization process. Now, this overall process is divided into two categories or two segments. One is known as front end of the line, that means of this particular fabrication process, the front end process, which refers to the fabrication of active and passive elements, and these elements include resistors, capacitors, diodes and transistors. That means, you are defining the active and passive components which are giving you desirable properties as a part of circuit. And second type is basically back end of line, which comprises of metallic layers which are used as an interconnect between these various components fabricated in the front end of the line. That means, in the front end you will be defining the components, and interconnection will be established once the definition of the components is being done, or once these components have been individually fabricated. Now, this interconnection as well as within the IC as well as external to the devices is the job of metallization. This is basically a process where we are depositing thin film of metal on the wafer surface. Now, primary metallization applications are again divided into three categories depending upon their suitability as far as your device what you call area is concerned. Now, first category what we say is the gate metallization. That means, in case of my MOS devices, I need a gate material which is basically comprising of metals, and you need to establish the gate contact also. So, for gate metallization also, which connects the base of bipolar transistor or gate in case of MOSFETs to the neighboring regions, and that is known as gate metallization. Second is known as contact metallization. Now, contact metallization is directly communicating or directly interconnecting the semiconducting area or semiconductor area with the outside world, or this is basically the contacts which are being established in the defined areas like drain contact, source contact, or in case of my BJT I will have emitter contact or base contact, all those contacts which are being established for connecting the or physically connecting the device to be part of the overall circuit, we call it as contact. And then comes the interconnect metallization. Now, this interconnect metallization is as far as your individual devices are concerned, as well as and the other components of the circuit are concerned. For example, you may fabricate multiple MOSFETs, or for complementary MOSFET device you will have NMOS and PMOS fabricated within the single wafer. Now, this NMOS whatever is being fabricated in this particular area and PMOS which is being fabricated in the area, we will be interconnected using the metallization, and these metallization layers we are going to see them. So, these are basically interconnect. So, that means you have three categories, one is gate, another is contact, and third one is the interconnect. So, these are the typical three areas or three categories of metallization which are essentially done in case of my integrated circuit fabrication. Now, in order to attain them, what are the desirable properties? Now, very first property of any material or any what you call contact, what you want to establish, it should be able to offer minimum resistance, and that is why the first is minimum electrical resistivity. The contact should offer minimum resistance to the conductivity, or it should have maximum conductivity, it should carry all the charge carriers through it, and therefore, this is the essential property. Secondly, it should be easy to form, or it should be easy to get deposited. That means, the process through which it is to be layered, the thin film is to be layered, that deposition process should be easy. Third one, easy to etch the pattern generation during the photo, like if you want to etch it for any particular reason, or if you want to carry out some modification into it, it should be easily getting etched away, or it should get easily deposited, eliminated by the proper processes which are being incorporated. Thirdly, next, okay, this was the third. Then next, it should be stable in the oxidizing ambient, it should not get oxidized easily and should not alter its properties. So, it should be stable. Secondly, it should be stable as well as should have minimum, okay, it should have good adhesivity property. And lastly, okay, and should have minimum built-in stress. Any stress, any mismatch in the layering or any not properly sticking up may result into the film getting torn off, or wear and tear can result, and that may have any discontinuity problem getting incorporated within the interconnects, and you do not want that to happen, and therefore, it has to be, it should have good adherence, it should get stuck up, or it should have good what you call property of getting like have good what you call sticking up, or it should get properly stuck up, should adhere, should get establish proper contact without any loss of connectivity. And lastly, it should have good surface finish. Any roughness may create charge or traps for the charges, and it can land up into, or you may not get, or the electrical property may get deviated, and you do not want that to happen. So, this is one of the important property. Another properties, or in continuation with it, you have, it should have stability throughout the processing steps, including temperature sintering or any variation, or you have dry oxidation, gathering, phosphorus or silica glass, or any other processes which are being carried out. Once you want to carry out some, like protective layer is to be deposited or something else to be carried out, it should have stability, that material which is being deposited should remain stable, it should not alter its properties. It should not have reaction with the final metal, that is aluminum. It should not contaminate the devices or the environment or the apparatus where you are carrying out the process. Now, suppose for example, I have done a process A where I have deposited particular material. Now, once I deposit particular material and I carry out process B, the material which was part of process E should not contaminate the wafer area, because of process B involves some elevation of temperature. So, you have to ensure that such kind of mismatch or such kind of what you call hazardous things do not occur or do not appear. So, you have to ensure that the material which is being selected while process A, because you know process B is going to be after process A. So, when you are carrying out process B, no material involved in process A should hamper or should alter the properties of the apparatus which is used in process B, or should not alter the or contaminate the material or wafer surface when process B is being carried out. So, you have to take care of this also. It should it should have good device characteristics throughout the device life till the time, that means the longevity of the device, good reliable operation from the device should be expected from it, because this particular metal contact should not alter the device performance. For window contacts, you need to have low contact resistance, it should have minimal junction penetration and low electromigration. The metal charges or metal electrons should not migrate or come out from their original position where they have been deposited. Even if you have large current flowing through that interconnect, the property of the interconnect should remain unaltered, thereby ensuring reliable operation from the device throughout the life span of the equipment or for the circuit for which that particular device is being designed or which is part of that particular circuit. Suppose I have an IC which is being placed, or it is a part of some big system. It should remain operational, it should remain it should function reliably throughout the lifespan of that particular system, because this IC is going to be part of that system. So, functionality of the system should not get hampered just because small interconnect within an IC has got dissolved or got the reliable operation has the operation got compromised and thereby the IC failed. So, there are some instances we encounter in our day to day lifespan. So, these are because of some failures in this such kind of failures only we encounter these kind of instances. So, you do not want that to happen. So, you have to take care of it, and these are the desirable properties which are expected. But remember that none of the material is giving you this kind of feature, none of the material has got all these desirable properties, because there is always a trade off. If you want to achieve something, something is going to get lost. So, you have to select the material wisely depending upon the application. So, what are those applications? Just see here, titanium silicide and titanium is being used, and here you are using those that is being used as an interconnect. So, this is the device where you are having p type wafer, here you are having p well where NMOS is being fabricated, here you are having N well where PMOS is being fabricated, see p plus diffusion, and this is the gate area where titanium silicide is being used. This is the interconnect from gate, just see source and drain, you are having metal contacts being established. These are basically these are the two drains, you can say if two drains are connected, this is my source, this is my source, these are drains and these are the gate contacts. Okay. So, this is how you have metal contacts, CMOS standard metallizations. This is another example where you will find different levels. This is the memory basically being shown. This is the this is the diffusion area, local interconnect. You will find different levels of contact. This is the word line, whereas this is the stud. So, you have different levels of metallization being incorporated for connecting different levels or circuit parameters. At one level you will have all drains connected, at another level you will have some other this one being connected. So, these are the window openings through which the metal contacts are brought up, and as many as 7 to 20 layers are there for the metallization, which constitute a complex which will make a constant complex circuit to function. All the interconnects, all complex interconnects will be brought out or will be their complexity will be resolved by incorporating them at multi-layer structure, and that is how you will try to attain multi-level metallization and carry out this particular job. So, this is what is known as So, this is one of the feature through which multi-layer metallization is being done. Now, here also there is multi-level metallization being shown. Here you are having metallization where it is the dominating process. AKtU alloy is normally being used, generally widely being used. This is the tungsten plug, okay, which was used in early 1890s, but there were some problems being issued. So, you will have you were using titanium as the welding layer, titanium nitride used for barrier because it has got very good adhesivity, but normally or since then, since the devices are being what you call shrinking, the speed of operation is getting enhanced. There were lot of issues related to the interconnects, and multiple materials have been explored by the scientists, VLSI designers, and finally, there were so many like different components or alloys of CU being used. So, most popular material which is being widely used is the copper. So, copper is converted into its alloy and it is being used widely or mostly. So, therefore, this particular comment is being done, that is future is CU. Now, what are the possible choices of metallization? We have seen the 3 zones. So, what are the materials which are being used for gate and interconnect and contacts? We generally use polysilicon, silicides, that is metal silicates or silicides we call them as. Then you have nitrides, then you have copper or refractory metals, aluminum, and combination of 2 or more of such materials like copper, aluminum and refractory metals such as other things, we are normally using them as gate metal as well as contacts. Now, for gate metal you have some condition that phi m and phi s, you know already, semiconductor work function related constraint, that if that is being made when you are doping the semiconductor. So, if that constant is being made, so that material will be wisely, or you need to choose the material which is being used for the gate very wisely, so that the metal work function should be higher than that of the semiconductor. Then diffusion barrier, for diffusion barrier we use titanium, titanium nitride, thallium, okay. Then you have some alloys, then you use silicides also. For the top level, topmost interconnect layer, you go for aluminum or copper. You need to selectively form the materials and you make use, or for silicon only, some silicides, tungsten, aluminum and copper. These are the popular materials which are being used. Now, what are the techniques which are being used for this metallization? So, one of the popular method or one of the popular technique what we have seen in the thin film deposition also is PVD or physical vapor deposition. Now, this physical vapor deposition is physically you are energizing the species or materials, whatever metal, you are evaporating it and allowing it to strike against the area where you want to deposit it. So, that particular material in evaporated form will strike or impinge onto the area where it is to be deposited, and then subsequently it is going to get form a layer onto the surface. So, this is one of the technique where physically you are making, or that kind of thing is basically a sputtering technique, which is normally or which is widely being used. This is mainly okay for all copper, aluminum and alloys. This particular method or sputtering or vapor deposition is the most common technique. Another one is the chemical vapor deposition, which is used only for polysilicon, for gate in the MOSFET, and tungsten, where we need to have metal plugs for trench lines. It is also used for depositing the barrier layers, that is silicides and nitride layers between silicon and copper. Similarly, electroplating is used. This is one of the other technique, like additional technique which is being used, where you have CU deposition which is known as Deposition process, or this is also one of the process where you carry out the electroplating of copper onto the wafer surface. Now, what is this physical vapor deposition? This is the chamber. You have seen this physical vapor deposition in the thin film also, When we studied thin film deposition, there also we were considering, but those thin films were of different materials. Here we are only restricting to the metallization materials or metals. So, metal thin films can be deposited using this particular chamber. It is a dome, what you call a vertical chamber, where you are this is a high vacuum pump which is making this material evaporation of the source material. Once the material gets evaporated, there will be high vacuum of 10 raised to the power 5 minus 5 to 10 raised to the power minus 7 tar, which is ensuring that there is no contamination inside and the deposition is uniform. Here you are having this planetary wafer holder which is holding those wafers. Here your wafers where the areas are to be deposited, those areas are exposed. Okay. And once the material is evaporated, it is made to strike with the purged gas, it is made to impinged on, or it is made to strike onto these material wafers, where uniform deposition, the alignment is such that there is uniform deposition. Okay. You have to ensure that the alignment, with proper alignment, these wafers are placed on the onto the wafer holder, so that there is uniform deposition onto the. Now, how that particular thing is being done, that is shown over here. You are having argon ions which are inert, they are used to what you call with forcibly, they are made to, like, they are along with the argon, these materials are being what you call projected, or they are made accelerated towards the material, or that is how the deposition is going to happen. These argon ions and these are the wafers. See, this is the target. Now, your ions will be activated and they will be allowed to strike and settle down onto the wafer, and this is how it will strike and your material will get deposited. This is what is this sputtering all about. Now, why sputtering is normally preferred? It is prevailed due to the following reasons. It has high deposition rate which is afforded by modern cathode and target design. Secondly, the ability, it has got good ability to maintain complex alloy compositions. It has got ability to deposit high temperature and refractory materials. It has capability to maintain well controlled and uniform deposition. You can have 200 mm or larger wafers also can be simultaneously used, or batch processing is also allowed, that is one of the biggest advantage. And it has got ability to in multi chamber system also you can have cleaning, in situ cleaning feasible, viable, and that is one of the important thing. The ability in multi channel system, multi chamber system to clean the contact before depositing. So, in situ cleaning is also viable, and that is why this particular method is predominantly used in my metal deposition. Now, another technique is the chemical vapor deposition, where we have seen already there will be chemical reaction, and it is good because of as far as large aspect ratios are concerned. Chemical vapor deposition has got advantages such as excellent step coverage. Step coverage is basically the area, that is horizontal and vertical deposition will be uniform, because there is chemical reaction involved and you can control that, and that is how you have larger throughput, and it is basically, since the chemical reaction is involved, you have got good like low temperature process, whereas in previous case like PVD, you are that those ions are impinged or they are made to strike. So, there can be the wafer temperature is also normally elevated, so that there is uniform deposition. So, these are CVD techniques is generally used for barrier deposition or barrier layer that separates the metal from silicon, and it has got very good large aspect ratios can be used, and that is what is the main reason for which it is being used. Now, if you compare CVD and PVD, we have seen that in case of CVD chemical reaction is appearing on the surface, whereas there is no chemical reaction in case of PVD. In case of chemical vapor deposition, you have better step coverage, then you have gap filling ability. The alloy has got, like CVD has impurity in the film, lower conductivity, and these are hard to deposit in like the technique is hard when you want to deposit the alloys. Whereas physical vapor deposition, there is no chemical reaction on the surface, poor step coverage and poor gap filling ability. but it has got very good quality of the deposited film. The film will have higher conductivity and you can have different alloys which can be deposited, that is what is its ability. Again, depending upon the deposition rate, evaporation will have better as far as your sputtering is concerned. Sputtering will have one atomic layer. So, evaporated species will be depositing very faster. Choice of material will be limited in case of my physical vapor deposition, whereas in case of my sputtering the choice of material can be, variety of materials can be deposited. As far as purity is concerned, evaporation will be better, whereas here sputtering may have contamination. Both physical vapor deposition techniques, but we are checking out how they behave. Surface damage, in case of my sputtering there is possibility of damage, whereas in case of my deposition which is normally done through evaporation, very less possibility of contamination. Alloy composition or stoichiometry, that is stoichiometry or the alignment of the crystal alignment, I say this, there will be no control as far as evaporation is concerned, whereas when you are sputtering it or writing with the atomic beam, it will be somewhat like light, a one atom will be deposited. So, you will have very good alignment. Changes in the source material are easy in case of evaporation, but in case of sputtering it will be very expensive, because you will have to change the atomic composition will be changing. So, all the parameters associated with the system will change. There will be, as far as uniformity is concerned, in evaporation it will be difficult, whereas in case of sputtering it will be good. Thickness control also you have very good control, adhesivity also excellent. So, overall these are the reasons which make sputtering one of the best what you call technique for metallization. So, sputtering is generally used, mostly recommended technique which is generally widely used as far as your metallization is concerned. The last technique what we saw is electroplating. It is the process commonly used for deposition of copper. The advantage is it is low cost, temperature requirements are less as compared to other vacuum deposition systems, and lastly it has got good average or moderate deposition rate as compared to your physical vapor deposition system, where atom by atom you are physically allowing them to layer like one by one. This much is better. Electroplating requires a uniform seed layer. So, initially you should have a seed layer based on which, if the seed layer is uniform, the electroplating also will be uniform. It is obtained by, this is also obtained by sputtering the seed layer with which is basically 30 to 200 nanometer thick. The reaction is twice, you have one anode, another one cathode, this is, and automatically electroplating, we have seen already electroplating like chromium plating and other things are being done. So, same is the process over here, you are having the deposited Cu, it will get CuSO4 solution, you will have anode and cathode, the material which is to be deposited will be placed on the cathode, the wafer will serve as a cathode and you can have deposition on it. The reaction will be 2 Cu plus plus, 2 Cu plus plus, reacting with 2 hydrogen molecules or H2O water molecules, giving us CuS, that is copper twice Cu solid, oxygen getting released and hydrogen also getting released. So, naturally the process is releasing hydrogen and oxygen, you have to be hydrogen whenever is released, you have to do the carry out lot of precautions, and that is how the electroplating is being carried out. It is basically a simple process when you want the uniform film at low cost. So, this is what is the preferential technique when you want to save as far as your economy is concerned and average film is to be layered. But best technique is your sputtering, which is most important and most what you call widely used. So, if your concept is clear, you should be able to answer, like we have seen in this lecture, what are the choices of materials, how the techniques are being used, that is we have seen the physical vapor deposition technique and the sputtering technique and chemical vapor deposition technique and electroplating. So, these are the 4 basically techniques which have been used. You should be able to answer the following questions. 1, you should be able to list the desirable properties of the materials that are used, describe the metallization applications which are in IC fabrication, compare CVD and PVD techniques used in the metallization. You should be also able to describe these materials. They can be like you someone can ask you, you should be able to know how the process happens. You should be able to elaborate the furnace structure schematic and should be able to elaborate these techniques. Once your concept of metallization is clear, that is it is similar to your thin film deposition. Once that is clear, we can proceed further with the other things. Thank you, good luck and God bless.